Hello, and welcome to the Watts Water CEU-approved presentation, Meeting New Water Quality Mandates in Healthcare Settings. This presentation will walk you through the new national standards that target reducing the risk of Legionnaire's disease. The content of this program is sponsored by Watts and was first published in Architectural Record magazine in 2017 as a continuing education course titled Meeting New Water Quality Mandates in Healthcare Settings. After this presentation, you should be able to identify and recognize the conditions that contribute to the development and growth of Legionella in healthcare facilities, identify the requirements of ASHRAE 188 and the new Department of Health and Human Services Policy Memorandum related to water quality in healthcare settings to reduce the risk of Legionnaire's disease. Assess the potential ways to address Legionella in water supply, distribution, and drainage systems in healthcare facilities. And specify products that can contribute to compliance with water quality requirements contained in the Department of Health and Human Services Memorandum and ASHRAE 188. This presentation will look at some of the concerns over Legionnaire's disease, the requirements of standards related to controlling or eliminating cases and outbreaks, and some of the fundamental design implications related to water-based systems in healthcare settings. Here is the agenda, broken down into 5 parts. We will start with a broad view of healthcare and Legionella bacteria and explore the cause of Legionnaire's disease. Next, we will look at some of the relevant ASHRAE standards related to preventing Legionella outbreaks. Third, we will review a new policy memorandum that applies to the majority of hospitals that could affect the receipt of Medicaid and Medicare reimbursements. Fourth, we will take a closer look at the typical water systems in a healthcare facility and how to address their management in relation to Legionella mitigation. So let's start off with the big picture of healthcare and Legionella. Hospitals and other healthcare facilities in general require water to operate, and usually a lot of it. It is used not only in patient room sinks, showers, and toilets, but also in staff sink and scrub areas, wellness rehab areas, food service centers, public restrooms, and laboratories. Additionally, water drives many of the mechanical systems in a facility, including HVAC systems, fire protection, and domestic water systems, both hot and cold. All of this water is intended for good outcomes, but can also be the primary cause of concern for unintended consequences, since water can be a prime breeding ground for bacteria and disease if not managed properly. Waterborne pathogens can be a threat not only to patients, but also to staff, visitors, and other people who come in contact with liquid water, vapor, or airborne spray in a healthcare setting. One of the most troubling of those pathogens is Legionella bacteria, which is the cause of Legionnaire's disease, a type of pneumonia that can lead to severe disabilities or even death. Its name comes from one of the first and most public discoveries of the condition, which occurred at the 1976 convention of the American Legion, where a number of attendees became sick and/or died. Since then, the Centers for Disease Control, or CDC, has investigated the condition at great length and recorded between 8,000 to 18,000 cases per year of people who have become infected in the United States. Obviously, they don't all make the news, but the concern is real and significant in healthcare settings. New standards and guidelines are now in place, applicable to designers, facility managers, and healthcare executives. Those tasked with managing and operating a successful healthcare facility typically focus on achieving some fundamental goals. These can include safety for their patients, employees, and the public, providing comfort for those within the facility, and appropriate efficiency in operations. Ultimately, the goal of everyone who works at or visits a healthcare facility is the overall satisfaction of the patient. When it comes to treating patients with Legionnaire's disease, also known as LD, all of these goals apply, so it is worth understanding a few fundamentals and statistics about the disease. Legionnaire's disease doesn't spread from person to person. Instead, according to ASHRAE 188, the bacteria spread through mist, such as from cooling towers, evaporative condensers, showers and faucets, whirlpool spas, decorative fountains, and misters. Those at most risk, according to the Mayo Clinic and other healthcare organizations, include persons who are at least 50 years old, smokers, or those with underlying medical conditions, such as chronic lung disease or immunosuppression. Many people exposed to Legionella bacteria don't develop symptoms, but those who do may experience cough, fever, chills, shortness of breath, muscle aches, headaches, and diarrhea. Legionnaires is essentially a form of pneumonia. According to Mayo Clinic, LD can be treated with antibiotics such as azithromycin or ciprofloxacin, assuming it is diagnosed properly and in time for the antibiotics to help. Consider these statistics reported from the CDC. Cases of LD reported annually in the U.S. from 2000 to 2009 increased by 217%. Measured from 2000 to 2014, the increase was 400%. The number of direct healthcare dollars it costs in the U.S. to treat a single case of Legionella is $34,000. The cost to the healthcare system for hospitalizations for 3 common waterborne diseases is $539 million annually, with Legionnaire's disease being the largest cost. According to claims management, the range of reported jury awards and settlements related directly to LD is $255,000 to $5.2 million. And keep in mind that reports of settlements are rare, as most agreements include stipulations that payout amounts remain confidential. While LD is clearly a potential source of income for care in hospitals, if the infection is contracted while someone is in a healthcare facility, it can have potential dire consequences on the continued operation of the facility. The CDC has investigated building-associated outbreaks of LD and determined that the most common places for getting the disease are hospitals, long-term care facilities, and hotels. According to ASHRAE, in these types of buildings, the source for spreading water droplets contaminated with Legionella can include shower heads and faucets, building plumbing systems, cooling towers, hot tubs, decorative fountains, and aerosolizing water features. If Legionnaire's disease is contracted while a patient is at the hospital may not get reimbursed for expenses related to their care. Based on the facts and statistics about LD that we have just covered, it is not surprising that national standards have recently emerged to provide guidance to hospital personnel, but also to design professionals in how to address this potential threat. We will look at the most notable ones developed by the American Society for Heating, Refrigeration, and Air Conditioning Engineers, otherwise known as ASHRAE. As a leading professional building engineering organization, ASHRAE has taken note of the connection between water-based mechanical and plumbing systems in buildings and Legionella bacteria growth. After reviewing the concerns and conditions, they first published a guideline in the year 2000 titled Guideline 12-2000, Minimizing the Risk of Legionellosis Associated with Building Water Systems. The stated purpose of the guidelines is to provide information and guidance in order to minimize Legionella contamination in building water systems. They have continued to review the guideline and in 2015 published an updated ANSI ASHRAE Standard 188, Legionellosis, Risk Management for Building Water Systems. This standard, which they suggest is essential for anyone involved in design, construction, installation, commissioning, operation, maintenance, and service of centralized building water systems and components, establishes minimum risk management requirements for building water systems to combat the Legionella bacteria. It not only includes a description of the environmental conditions that promote the growth of Legionella, it also outlines action plans for managing and monitoring those conditions. Additionally, there are informative annexes and a bibliography that contain suggestions, recommendations, and references for additional guidance. ASHRAE 188 begins by pointing out that while Legionella bacteria occur naturally in freshwater environments, they become a health concern when they grow in building water systems that are not adequately maintained. It also recognizes that the mere presence of Legionella in a water system or device is not sufficient to cause disease. Rather, to cause illness, the bacteria must ultimately be inhaled or aspirated into the lungs of a susceptible person. Nonetheless, there are enough incidences of that happening to warrant a concerted effort to prevent Legionella growth in buildings. A key focus of ASHRAE 188 is to assist designers and building operators in developing a specific water management program for the systems that exist in their building or campus. It recognizes that design, good operations, and maintenance procedures that prevent growth and spread of Legionella are regarded as the best methods of preventing disease. In fact, CDC investigations of outbreaks show that 9 out of 10, or nearly all of them, were caused by problems preventable with more elective water management. Developing a water management program, therefore, with the recommended practices can definitely reduce the chance of bacterial colonization, amplification, and dissemination to people. Of course, no program can guarantee that a system or individual component will be totally free of Legionella, but it should be able to keep it down within acceptable limits. Creation of a water management program under ASHRAE 188 includes a 7-step process. The first step is to create a program team. The people responsible for the development and implementation of the program need to be identified. This will necessarily include a design professional familiar with the design and operation of all the water systems in the facility. Suggested team members include infection prevention personnel, a Legionella expert who could be a consultant or equipment manufacturer, upper management personnel with decision-making authority, and facility management. Overall, the key is to bring the right people together to follow the process and develop specific procedures for a particular facility to adopt and implement. Within this framework, ASHRAE 188 articulates the requirements for surveys to identify building water systems in detail and to state specific criteria that need to be incorporated. There is also a specific section covering requirements for designing building water systems, and one specific to healthcare facilities. Like all standards, ASHRAE 188 is a voluntary consensus standard that may or may not be adopted into local plumbing codes. If it is made part of the code, the local authority having jurisdiction most likely performs enforcement. Otherwise, it may be adopted by a local healthcare organization or used to support certification or accreditation of the facility. With a basic understanding of the ASHRAE standards related to Legionella, let's turn to one of the agencies that has adopted them, namely the people who provide Medicare and Medicaid reimbursement to healthcare facilities. The Department of Health and Human Services, known as DHHS, and the Centers for Medicare and Medicaid Services, known as CMS, are the arm of the federal government that provides funding and oversight for facilities and care providers administering to patients using Medicare or Medicaid insurance. In June of 2017, they developed and released a new policy memorandum titled Requirement to Reduce Legionella Risk in Healthcare Facility Water Systems to Prevent Cases and Outbreaks of Legionnaires' Disease. This policy memorandum applies to hospitals, critical access hospitals, and long-term care, but it is intended to provide general awareness for all healthcare organizations. Under this policy memorandum, CMS now requires Medicare-certified healthcare facilities to have water management policies, management teams and procedures in place to reduce the risk of growth and spread of Legionella and other opportunistic pathogens in building water systems. The basis for these policies and procedures is ASHRAE Standard 188, and in 2016, the CDC and its partners developed a toolkit to facilitate implementation by facilities. This toolkit can now be found at the link shown here. The toolkit describes the environmental, clinical, and epidemiologic considerations for healthcare facilities related to Legionella. It also provides suggested logistics of establishing a water management team, conducting surveys, and developing and implementing a water management program per ASHRAE 188. It includes control measures such as physical controls, temperature management, disinfectant level control, visual inspections, and environmental testing for pathogens. Of particular note to healthcare executives, facilities are expected to comply with the CMS requirements to protect the health and safety of its patients. Those facilities deemed unable to demonstrate measures to minimize the risk of LD are at risk of citation for noncompliance with the CMS conditions of participation. The CMS policy memorandum indicates clearly that accrediting organizations will be surveying healthcare facilities deemed to participate in Medicare for compliance with the requirements listed in this memorandum, as well, and will cite noncompliance accordingly. Based on this, it is expected that all healthcare facilities will have a renewed interest in establishing and carrying out a full water management program based on ASHRAE 188 and the CMS policy. We have covered the nature of the health issue with Legionella, the 7-part process of the ASHRAE Standards, and the federal agencies that are making water management for reduction of Legionella a requirement for funding. Let's now turn our attention to the specific parts of a water system in healthcare facilities that need to be addressed. The first overriding issue in looking at water systems and Legionella is the direct relationship between bacteria growth and water temperature. The ideal range of temperature for such growth is 95 to 115 degrees Fahrenheit, but bacteria are known to grow and be active anywhere between 68 to 122 degrees Fahrenheit. Below 68 degrees, Legionella bacteria can survive but are dormant, while above 122 degrees, they can survive but do not multiply. The bacteria will die slowly when temperatures in the water reach 131 degrees Fahrenheit and die rapidly between 158 and 176 degrees. Most commonly, LD outbreaks are linked to temperature-appropriate environmental reservoirs in large or complex water systems, including those found in healthcare facilities, such as hospitals and long-term care facilities. When water is moved or sprayed into the air, such as from shower heads, cooling towers, hot tubs, and decorative fountains, transmission of the Legionella bacteria to humans is possible. Further, Legionella can grow in parts of building water systems that are continually wet and within temperature range suitable for growth. Since a building water system contains many different subsystems and components, we will review some of the major ones, with a discussion of the relevant approaches to identifying Legionella hazards and control methods. Addressing each of these water quality issues at the source is the best way to assure that the water entering a facility does not have the potential to introduce or contribute to waterborne bacteria development and growth. The different subsystems include water supply, cold water distribution, water heating, hot water distribution, and waste drainage. Most healthcare facilities rely on a public or municipal water source, which has likely been treated in a centralized plant and piped through public water supply lines. The water leaving the plant has certainly been tested and maintained to prescriptive levels for portability and human health. But there is no guarantee that its trip through an aging piping system will keep it that way. Waterline breaks, outdated joint connections, dissipation of chemicals, and other conditions all have the potential for contaminating municipal water delivered to a building. Therefore, several water supply components deserve particular attention. Among the common approaches to protecting water quality in a water supply system, the use of backflow preventers is typical. Backflow systems are essentially a series of plumbing control valves that prevent the reverse flow of polluted water from entering into the potable water supply due to back siphonage or back pressure. While backflow preventers may not have a direct relation to Legionella control, they should be part of a control measure in a water management program. When selecting backflow preventers, there are choices to consider. Stainless steel versions are available as basic or mid-term products with some limited options. More robust and durable choices include ductile iron valves, some with epoxy-coated paint on the exterior and designs for continuous or heavy usage. One of the things that can alter performance of any water system is the water operating pressure. Water coming in from a municipal system may be affected by other buildings, as well as by the level of demand in a healthcare building. If the pressure is too high, some parts of the building water system may not work well or can be damaged. If the pressure is too low, the water may not flow as intended and may lead to conditions that are conducive to Legionella and other biofilm and bacteria growth. The remedy is to install a valve to regulate the water pressure in the building. There are two fundamental choices in this regard. The first is a conventional water pressure reducing valve, or WPRV, which reduces fluctuating high inlet pressure to a constant lower outlet pressure. Such WPRVs typically have a broad range of flow potential and can be fully adjustable. For example, a municipal water system that is providing water in the 80 to 100 psi range could be regulated to a constant 50 psi with an appropriately sized and set WPRV. Further, smaller WPRVs could be located within an overall system to be set for different settings to suit the optimal pressure needs of different parts of a healthcare facility. The second option is to use an automatic control valve, or ACV, which provides the same function but is designed and constructed differently. The primary operating difference between an ACV and a WPRV is the flow rate in gallons per minute, or GPM, compared to the pressure in the system. Using a WPRV, the pressure will decrease as the flow increases. However, with an ACV, the pressure can remain fairly constant even as flow rates reach up to about 250 GPM. These are typical ACV applications in a commercial building. We show a high-rise, but you will also find ACVs in schools, hospitals, and other commercial buildings where a wide range of flows at a very consistent pressure are desired. One item related to flow rates is the current code requirement for many faucets and fixtures to operate in low flow conditions for the purpose of conserving water. This is good for water use, but can cause water to pool or sit in systems longer than otherwise desired to control Legionella growth. Low flow can lead to stagnation and increased scale. Scale that is built up inside piping serves as food and a breeding ground for the increase of Legionella bacteria. Therefore, water pressure control valves and low flow fixtures need to be an integral part of the water management program. With any uncertainty over the quality of the water entering a building, many healthcare facilities are being proactive and using a centralized system to at least filter, if not fully disinfect, the incoming water. Of particular relevance is an ultraviolet disinfection system, which is highly effective at providing protection against microbiological contamination in water. These systems are attractive not only because they can be very effective at killing microorganisms such as Legionella bacteria, but also because they are fairly simple to use and operate. Connected to a power source, they produce UV light that is projected onto the incoming water without the need for any chemicals to be handled or added to the water. For large systems, they are commonly completely enclosed for safety to prevent any accidental UV exposure to people. They also typically have sensors indicating their use and performance levels, and can be specified to operate efficiently by only turning on when there is actual water flow in the supply line. In order for UV to be most effective, the overall solution should also include some kind of filtration solution that reduces sediment and scale in the water. If the water is turbid when it passes through the UV light, the light might hit the sediment or even the shadow of the sediment instead of contacting the water molecules. Sediment and scale must be limited to have a very effective UV solution. It should also be noted that as with chemical injection and heat, UV cannot guarantee that Legionella will not grow as water goes further through a piping system, making a point-of-use solution also a vital part of your overall Legionella mitigation plan. Of course, there are other ways to disinfect water systems too. Some of the more accepted methods involve copper-silver ionization, chlorine, and other chemical treatments. Copper-silver ionization is known to be very effective at killing Legionella. However, it can come at a high cost and with high maintenance requirements. Chlorine and other chemicals have been utilized for Legionella and other bacteria control. The main disadvantage to chlorine is that it can be very corrosive to piping and other equipment. In cases of hyperchlorination, corrosion can cause pinholes to develop in piping. And as mentioned before, heat can also assist in the control of Legionella. Scale is related to potable, clean drinking water that has a high mineral content and is referred to as hard. Over time, the minerals can attach to the metallic surfaces of a water system and start to build up. The resulting scale often becomes encrusted on the internal moving parts of valves and components, affecting their intended purpose and potentially causing safety failures. In a boiler or hot water tank, heating elements can become coated with scale, reducing system efficiency and safety. In pipes and other components, scale can restrict water flow and create potential breeding grounds for bacteria. The solution here is an anti-scale system. A conventional system typically relies on the use of salts that need to be constantly replenished into the system as water flows through it. Salt also has a very large footprint. An alternative is to use a template-assisted crystalline, or TAC, system which eliminates the need for salt, takes up less square footage, and is generally regarded as much more economical with similar results. While reduction of scale and sediment doesn't directly kill Legionella, it makes all other Legionella-reducing solutions work more effectively. Some of the water used in buildings is not for direct contact with people, but is used instead for heating and cooling systems. Hydronic heating systems with boilers, for example, use water storage tanks to balance out the water requirements of the system. That water could be a breeding source of bacteria if the temperature conditions and other circumstances such as scale are favorable. Once the water is in the facility, it needs to be distributed appropriately for use on demand. Depending on the size and nature of the facility, that may prove to be rather complex, which is why the schematic flow diagram of a water system is important as part of a water management program. We will look at some of the common components of a distribution system here. Some facilities with high water flow requirements will use an on-site water storage tank to buffer the demand with the usage. That is an appropriate and time-honored method, but keep in mind that such tanks can also be a breeding ground for Legionella and other bacteria. Therefore, the temperature of the water should ideally be kept below 68 degrees Fahrenheit to keep Legionella dormant without the risk of activity. Water in a hot water tank is generally kept at an appropriate temperature for warm or hot water use in a building at around 110 to 120 degrees Fahrenheit. Unfortunately, that temperature is also in the ideal range for Legionella bacteria to grow and thrive. If the temperature hasn't been appropriately raised to the ASHRAE recommended 140 degrees Fahrenheit to kill Legionella within 30 minutes, there is the risk of bacteria growth. This will need to be addressed and monitored. Constant movement in tanks can reduce the growth of scale and thus help mitigate Legionella growth. There are also tankless options that can be considered. While heating water to the rapid kill range is one of the most effective and reliable control measures for dealing with Legionella, it is not necessarily the best temperature for water to be used by people. On average, any water that is above 106 degrees Fahrenheit will cause scalding and pain in humans, while water that is 140 degrees Fahrenheit can cause third-degree burns in a matter of seconds. 131 degrees Fahrenheit is the minimum temperature that is required to kill Legionella bacteria in a water heater. 106 degrees Fahrenheit is the average water temperature that causes pain. It takes only 2 to 3 seconds for a child or elderly person to receive third-degree burns from water at 140 degrees Fahrenheit. There are between 3,000 and 4,000 scald cases in the United States each year. For safety reasons, plumbing codes limit the maximum temperature exiting a fixture at 120 degrees Fahrenheit with the expectation that people can readily control the mix of cold and hot water at the faucet to meet their needs. However, there are plenty of things that can change the water temperature coming out of those faucets. For example, it is common for a healthcare building to use a recirculating system that pumps hot water uniformly through the hot water piping to prevent long wait times for heated water at a faucet. However, things like pressure fluctuations can cause hot and cold water to move less predictably through the system, while valves in the system could malfunction or fail. Mixing valves help compensate for those discrepancies and deliver a more predictable water temperature output. Clearly, there is a need to meet both the needs of killing Legionella with higher temperature water and the human requirements of a lower safe temperature. The solution is found in the use of tempering valves or mixing valves that blend hot water with cold water in a controlled manner. This ensures constant, safe outlet temperatures while minimizing the occurrences of both scalding and Legionella. There are two fundamental types of mixing valve systems: point of source and point of use. A point of source, or POS system, locates valves at or near the water heating source and typically has a higher capacity for controlled temperature water. A point of use, or POU system, uses multiple smaller mixing valves at or near plumbing fixtures, such as showers, lavatories, whirlpools, and emergency fixtures. Beyond purely thermostatic mixing valves, computerized digital mixing systems are also available that are considered a smarter and safer way to deliver mixed water throughout a healthcare facility. In this type of system, intelligent control modules and electronically actuated valves are used to allow faster and more accurate response to constant changes in the mixed water delivery demands. Further, digital water mixing and recirculation solutions can be integrated into a building automation system to allow facility managers complete control of and visibility into their domestic hot water delivery. As a point-of-source system, a digital mixing station can provide precise control of hot water delivery within 2 degrees of the set point, surpassing industry standards. Further, it eliminates temperature creep within the system, thus eliminating the need for balancing valves. In particular, a sanitization or disinfectant mode can be triggered to briefly raise the temperature above 158 degrees Fahrenheit to induce a rapid kill and purge all Legionella bacteria. At the same time, the digital mixing system can control temperatures leading to faucets, showers, and other outlets to reduce the risk of scalding in the mixed water. If combined with separate point-of-use protection, the digital mixing system allows for continuous elevated circulation temperatures to prevent Legionella per ASHRAE and CDC guidelines. Concurrently, the digital mixing system can control the circulation pump to prevent stagnant conditions or maximize flow rates. Finally, since most large facilities use some type of building automation system, a digital mixing system can be linked to the larger system to communicate and control temperature, pressure, flow, and energy consumption as part of an overall operations and maintenance plan. It also makes documentation and verification more straightforward and available in a water management program as called for in ASHRAE 188 and the CMS mandate. If all of the measures described thus far are followed, then the water flowing through the distribution piping, valves, and fittings should be fairly safe. But that doesn't mean they don't need to be checked, inspected, and verified as part of the water management program. Valves of all types can be a concern, so working closely with manufacturers to identify and specify those that are most suitable for preventing problems and growth is appropriate. Point-of-use fixtures are where people come in contact with water throughout the healthcare facility. The primary concern is that a biofilm can start to form on edges or within components of a faucet or wash station. If bacteria are allowed to build up in things such as aerators or faucet flow restrictors, it could grow and, worse, be sprayed into the air and cause illness. That means such components need to be checked, cleaned, or replaced regularly. A related concern is the location of wash fixtures and the potential for water splashing onto either people or equipment used to treat patients. Separating sinks and other water stations from medication dosing areas and equipment is one way to help minimize the possibility of cross-contamination. Splash guards around sinks and scrub areas can also be elective in some areas. It should also be noted that after a fixture has not been used for some time, water may collect and sit within the piping of such fixtures. This water can become stagnant and a breeding ground for Legionella growth. Showers and hoses pose additional concerns since biofilm formation can be particularly problematic here. Handheld showers are common in healthcare facilities, but the hose portion can hold water between uses, and the shower head itself can remain warm and moist, allowing bacteria growth. The recommendations here include allowing the hoses to hang down and drain after each use. It is also prudent to replace handheld showers periodically. Point-of-use filters are also a consideration for both faucets and showers. The final part of a water management program includes attention to the drainage system in a building. Since virtually all of the water flowing through a facility is used and then drained away, the drainage system needs to be free of Legionella and other bacteria as well. This means that water must be freely draining, with no opportunity for stagnation or biofilm formation here either. When it comes to drainage piping, non-porous materials are preferred in healthcare facilities. Porous materials, such as some metals and plastics, can become unintended breeding grounds for bacteria growth. Significantly lower growth of bacteria has been found on stainless steel, making it the ideal solution for applications where hygiene is a concern, particularly in kitchens and food service areas of healthcare facilities. Outbreaks of illness, particularly Legionnaire's disease, can be dramatically reduced in healthcare settings if proper attention is paid to the important aspects of water management. The protocol and requirements of ASHRAE 188 and the CMS mandate are recognized by facility managers and governmental bodies as the best place to start, since it is based around a comprehensive and continuous water management program. In fact, continued accreditation and funding for a facility under Medicare and Medicaid depend on it. Reviewing and addressing all components and opportunities in the supply, distribution, and drainage portions of a building water system is needed to produce a proper program. Ultimately, it is the collaboration of design professionals, facility managers, equipment suppliers, infection prevention professionals, and others that allow for the successful development and ongoing monitoring of a water management program. Watts Water Technologies, dedicated to improving the comfort, safety, and quality of life for people around the world. Through our industry-leading brands and our expertise in a wide range of water technologies, all of Watts' brands come together to serve your needs.